Hello everyone, welcome to Control Systems lectures. In the previous lecture, I had discussed about the time response analysis of second order system, where we took the case where we had the input as the step input and we took the value of zeta as between 0 and 1, so that became the underdamped case, and the second case we took the value of zeta as equal to 0, so that was the undamped case. So we saw the response of the system there. In the case of underdamped system, the system exhibits oscillation plus damping, whereas in case of undamped system, there is no damping and the system is continuously oscillating in nature. Now, in today's lecture, we are going to study about critically damped and overdamped case. We are going to see how the plot will look when we apply step input to these systems. So the first case that we are taking is critically damped system. In case of critically damped system, the condition is that the value of zeta should be equal to 1. So this is your standard second order system. The standard second order system has the forward gain as omega n square divided by s into s plus 2 zeta omega n. The feedback path is taken as 1. So if you find out the overall transfer function for this, you get it as omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now we are taking the case where the system is going to be critically damped in nature. Hence the value of zeta will be equal to 1. Substituting this value in this transfer function, you will get omega n square divided by s square plus 2. The value of zeta is 1, hence it will become 2 into omega n s plus omega n square. Right? Now just observe this. Just observe the denominator. Denominator is of the form a plus b ka whole square. A square plus 2ab plus b square. So it's taking the same form. Hence we can write this as omega n square divided by s plus omega n the whole square. A plus b the whole square. Hence s plus omega n the whole square. Okay. Now we have to find out the time response of the system when we apply the input to the system. The input that we are going to apply is going to be step input. By step input we mean that it's going to be 1 by s in the Laplace domain. So the output can be written as multiplication of input and the transfer function, the overall transfer function. If we take the input as 1 by s, the transfer function we have already derived as omega n square divided by s plus omega n the whole square. So this is going to be the output in Laplace domain, or we can say it as the S domain. So this is the output in S domain. Okay. Also, if I want to plot the poles for the system, the plot for poles of the system, where are these poles, input pole and the pole for the transfer function or the system, where are they going to lie? So in the S plane we have the real axis sigma and the imaginary axis as j omega. So we are having two poles actually. From this transfer function we can see that system is having two poles. System is having two poles, okay, and they are lying where? They are lying, both the poles are lying at minus omega n. So I am going to have two poles, double poles. Both the poles will be lying at minus omega n. Okay. In the previous lecture, in one of the lecture, I had told you that when you have got real poles, then the system will have exponentially decaying nature and system will be stable, but there are going to be no oscillations in the system. We can also plot this inputs pole. So inputs pole is going to lie at the origin. So I am having a pole due to the input which is lying at the origin. Fine. Now I want to plot actually the graph of the output in time domain. But what I am having over here, it is in the S domain or the Laplace domain. So to convert this into time domain, I will have to take the inverse Laplace of it. And to take the inverse Laplace, first of all I have to transform this function in such a way that the inverse Laplace of it can be taken. So the best way to do it, the way to do it is to use partial fraction method. So we'll say that the CS can be written in partial fraction way. So it will be A divided by S plus, as you can see that there is a perfect square over here, so I can write this as s plus omega n the whole square plus c divided by s plus omega n. Okay, now you can do the partial fraction for it and find out what are the value, what will be the values of a, b and c. So to find the value of A, you will have to substitute the value. This is actually equal to omega n square divided by s into s plus omega n the whole square. To find the value of A, substitute s is equal to 0 in the main equation, keeping aside this s. So you'll get the value of A as equal to 1. So this A will actually become 1 divided by s. To find the value of B, substitute the value of S as equal to minus omega n in the main equation, keeping aside this S plus omega n, the whole square term. So it will become omega n square divided by minus omega n. So that will become minus omega n. So value of B is going to come as minus omega n divided by S plus omega n the whole square. And to find the value of C, if you want to find out, the method is that you take the differentiation of the term which is apart from this square term. Okay, so you will just differentiate omega n square divided by s, do the differentiate it with respect to s. Okay, and when you differentiate, then keep, after differentiating, keep the value of s as equal to minus omega n. So when you do it, it is actually omega n square is a constant. So we can take this out. So the differentiation of 1 by s will be minus 1 by s square. Keep the value of s as equal to minus omega n. Hence this c value is going to come as minus omega n square divided by omega n square. So the value of c will come out to be equal to minus 1. Hence we can write the value of c as minus 1 divided by s plus omega n. Now this function is in the form that we can take the Laplace inverse transform of it. So if we take the inverse Laplace transform of it, the value of Ct can be derived as 1 divided by s is ut, okay, minus omega n divided by s plus omega n the whole square. So as it is, omega n is a constant, and upon s plus omega n the whole square, 1 by s square form. So it will be actually t, but t multiplied by, as s plus something is added over here, so it will be e to the power minus omega n t. So inverse Laplace of omega n divided by this is going to be omega n plus omega n into t into e to the power minus omega n t, minus Laplace inverse of 1 divided by s plus omega n, it's e to the power minus omega n t. Okay, so I can write this as, I can take this ut can be actually written as 1. For the complete term, ut will be multiplied. So I can simply write this as 1 minus, I'm going to take e to the power minus omega n t outside this, outside the bracket. So what we'll get t into omega n plus 1. This is the term that we are getting over here. Now, will this system, is this system going to exhibit any oscillations? Can you see that whether, can you identify whether the system is going to exhibit any oscillations? Oscillations will come when the system is having some sinusoidal components in it. But here we can see that the system is having exponential component and this ramp t signal in it. And these two signals actually they are getting multiplied in it. Okay, so the system won't have any oscillations in it. If you want to find out what is going to be the value of system at t equal to 0 and t equal to infinite, then just substitute these values in this equation, that is Ct. Okay, just substitute at t equal to 0, this is going to be 1 minus e to the power minus 0 multiplied by 0 into omega n plus 1. So 1 minus e to the power 0, this is going to be 1 multiplied by 1. So it's going to be 0. At t equal to 0, the value of Ct is going to be 0. At the value of Ct at t tending to infinite, that means when the system is going to achieve steady state. So when this happens, this is going to be 1 minus e to the power minus infinite multiplied by this infinite into omega n plus 1. Okay, so this complete term will reduce to 0, and hence at Ct, when t tends to infinite, this is going to attain the value of 1. Okay, so if I want to plot this curve, if I want to plot the curve for this critically damped case, then I can do it. I can plot the curve with respect to time. If I want to plot the Ct, first this exponential multiplied by t into omega n. So you can actually, if you want to see the behavior, you can actually take a few values of it of time, and you just substitute it, and then you'll find that the output, it looks something like this. Okay, so the output will look something like this, where at t tending to infinite, okay, the final steady state that we call it, so this is going to be, this value is going to be 1, and at t equal to 0, this value is equal to 0. So this is how your system's response is going to look like, and you can now relate it to, it's more or less similar to the first order response. In the first order system also, when we had applied unit step function to it, we had seen that we got a similar response there also. Okay, so this is how the response is going to look. It's not having any oscillations, unlike your underdamped case. In underdamped case, you had oscillations, and finally the system was settling to the steady state. But here you can see that there are no oscillations. The system is starting and it is finally reaching the steady state. There are no oscillations in it. If you want to find out what is going to be the time constant for it, or for this system, okay, so the time constant, I have already told, the time constant for any system, it can be found out if you take the inverse of the real part of the pole. So the poles over here, they are lying at which position? Poles, we had two poles for this system. We had got two poles for the system. Both the poles were lying at minus omega n. So my time constant can be found out as 1 divided by the real part of location of poles. So it's going to be 1 divided by omega n. This is going to be the time constant for this system. Okay, I hope this is clear. So this is the case for critically damped system. Unlike your underdamped system where you had oscillations, or the undamped system where also you had oscillations like this. So in this case you don't have any oscillations in the system. Now the next case, the fourth case that we are going to take is for the overdamped system. So the case 4 is going to be overdamped case for the same system. Overdamped case for the same second order system. So we have got the same system. For overdamped case, the value of zeta, extremely sorry for this. Value of zeta, it's actually greater than 1. So what will happen when this value of zeta will be greater than 1? We have seen that the transfer function for the system, it is given as omega n square divided by s square plus 2 zeta omega n s plus omega n square. Hence the poles for the system S1 and S2, they will lie wherever the roots of this equation will lie. So the poles of the system, we can write them as minus zeta omega n plus minus omega n under root of zeta square minus 1. We'll write it in this form, and here the value of zeta is going to be greater than 1. Hence, over here you can see that this under this root part, as zeta will be greater than 1, hence this is also going to be a real part. This is also going to be a real part. It's not going to be an imaginary number as we were getting in case of underdamped system. So from here you can see that minus zeta omega n plus some again real part or minus again some real part. This complete thing is going to give me some real poles only. So the output that we are going to get over here, they are going to be some real poles only. We are not going to get imaginary poles in this case for overdamped case. Okay, so I can say that the two poles, there are going to be two poles for the system, and those two poles, okay, this is S plane, so there are going to be two poles for the system. I can write this as P1. Both the poles, are they going to be same like in the case of critically damped case? No, the two poles that we are getting, they are not going to be same. One is minus zeta omega n plus this part omega n under root z square minus 1. Another is going to be minus minus. So I can write that there are two poles, and both the poles are real in nature and they are unique in nature. They are not same, they are different. Okay, so this and of course then find what do we want to find out. If we have this underdamped case, then we want to find out the response of the system. So the response of the system, again we are taking that the input is going to be unit step, and this we'll be multiplying it with the transfer function of the system. If I write this Rs as 1 by S, then this multiplied by the overall transfer function. The overall transfer function, you can see it's omega n square divided by s square plus 2 zeta omega n s plus omega n square. Or if I want to write it in terms of if I want to write this denominator as representing the roots of the system, then I can also split it in such a way that it will be omega n square divided by one pole is lying at S plus zeta omega n minus omega n under root of zeta square minus 1 multiplied by second root is lying as S plus zeta omega n, okay, plus omega n under root z square minus 1. This I can also write the same, this thing and this thing, these are same. I've just split मैंने इसको बिल्कुल split कर दिया है इसके roots के form में. Okay, so I can write the same thing in this form also. Again, if you want to find out the time response, then you will have to take the this complete function. You will have to take the inverse Laplace transform of it. To find the inverse Laplace, this has to be split in partial fractions. So I can write this equation as a divided by s plus b divided by first root. I'll write s plus zeta omega n minus omega n under root of z square minus 1. Third root I can write as c divided by this complete thing, okay, plus omega n under root of z square minus 1. So this is how my output will look like if I use the partial fraction method. And after you split it, if you find the value of a, b and c, this is a very simplest case of partial fraction, then you can easily take the inverse Laplace transform of it. So to find the value of a, you'll have to keep the value of s as equal to 0 in this equation, keeping aside this term. To find out b, you'll have to keep the value of s as equal to minus of zeta omega n plus omega n under root of z square minus 1 in this equation, keeping aside this complete term. Similarly, for c, you'll have to substitute the value of s as equal to this same thing. Okay. omega n minus omega n under root of z square minus 1, keeping aside this. So at all the values of s that you have, you will have to substitute it. When you substitute it, then you will get the value of a, b and c. Okay, I'm not doing this, I'm going to directly show you that what is the response that you will get. So the response that you will get, it's going to be 1 divided by s. Okay, so 1 by s will be, if you take the inverse Laplace, then it's going to be 1, of course multiplied by ut, minus e to the power, because this is something, this will get some constant divided by s plus something, so we'll get exponential term multiplied by the constant term. So exponential term is going to be e to the power minus zeta plus omega d multiplied by omega nt divided by 2 under root of z square minus 1 multiplied by zeta minus under root of z square minus 1. So when you substitute the value of s, you find out what is b and c, then you will get this complete term when you take the inverse Laplace. Similarly, for c, just do it for yourself, then it will give you a better picture. It will be e to the power minus z minus omega d into omega nt divided by this complete thing. Okay, this thing and this thing, they are actually going to be same. So z square minus 1 multiplied by zeta minus under root of zeta square minus 1. This is the output that you are getting for overdamped system. Now can you visualize this? You have got three terms over here. One, I can write this as the CT can be written as, this is first term that I can write as CT1 minus I am having some other term that is CT2 plus some other term that is CT3. So I am getting three terms over here. Okay. We had two poles, we had two real poles, and hence as poles were real, hence we got two terms which are exponentially decaying terms. Okay, if I want to plot this, then it's you can easily picture it. It's going to be something like this only. Okay, the value of CT is going to be something like this only. Why? Because I have got two exponentially decaying terms. So both will have, one will decay faster, another will decay slower. But if I add this one with these two, anyways whatever the output that I'll get, it will come out to be something like this only. Okay, this I can think intuitively that the output that I'll get for this one, it's going to come something like this only. Just do it. And here also we have minus and plus, so the best way to analyze this is that you just take a few values of t, take it as 0, take it at t equal to 0, take it at t equal to infinite, and take it at some t value in between these two instants, and just visualize, you can visualize that how this output is going to look like. Okay, so it will look like this only, because at t equal to 0, this is going to be 0. At t equal to infinite, it's going to attain the value as equal to 1. And as there are no oscillatory expressions in this complete equation, hence there are going to be no oscillations in the output for the system also. So this is how this output is going to look like, and this is what your overdamped system it will look like when you apply unit step input to it. Okay, if I want to find out the time constant for this function, the time constant for this case, then the time constant is defined as the reciprocal. I can find it from the reciprocal of the real part of the pole of the system, pole of the system. Okay, but here we had seen that there are two poles in the system. We have got two poles, one at P1, another is at P2. Okay, so if I am having two poles with real part, hence I can say that there are going to be two time constant, one at 1 by P1, another at 1 by P2. एक सिस्टम के दो टाइम कांस्टेंट होंगे. Okay, and we know that if I have got a pole like at at this point p1, okay, so this is going to contribute to the exponential part. Okay, इस पोल की वजह से क्या होगा, सिस्टम में एक एक्सपोनेंशियली डीकेइंग कर्व आएगा. ठीक है, ड्यू टू पोल p1. Why? Because I can write this pole as because this is a pole, I can write it as 1 divided by s plus p1. Okay, 1 divided by s plus p1. Due to this pole I can write it as in Laplace domain it will be 1 divided by s plus p2. ये सेम चीज़ जो हमने ऊपर निकाली है, हमारा सिस्टम जो था, सिस्टम में क्या था, 1 डिवाइडेड बाय एस प्लस समथिंग, 1 डिवाइडेड बाय एस प्लस अनदर समथिंग. ठीक है, दो पोल्स थे, तो इसको जनरलाइज वे में लिख रहे हैं 1 डिवाइडेड बाय एस प्लस p1, 1 डिवाइडेड बाय एस प्लस p2. And due to this we have seen that p1 is producing some constant multiplied by e to the power minus something decaying term plus p2. Okay, this will be p1t, and due to this we'll have some constant multiplied by e to the power minus p2t. So in the output that we are getting, we are having two exponentially decaying terms. One is e to the power minus p1t, another is due to e to the power minus p2t. Now if I want to plot the graph of these exponentially decaying terms, so I can say that one of the pole which is more nearer to this origin, this is going to decay slower. Okay, the decaying of this is going to be slow, whereas the pole which is far away from the origin, this is, if I'm saying it as p2, so the decay of this p2 will be faster. ये faster decay करेगा, ये slow तरीके से decay करेगा. Okay, so if I have two time constants and one of the time constant is due to p1, another is due to p2, तो हमको इसमें से कौन से टाइम कांस्टेंट को चूज करना है. Okay, which one to choose for this? The time constant due to p2, I'm saying a statement that the time constant due to any pole which is further from the origin, this should be neglected. Like if I am having p2 which is further from the origin, the nearer pole is at p1, the farther pole is at p2, then I should neglect this p2. क्यों? क्योंकि ये जल्दी डीके कर रहा है और सिस्टम में जो आउटपुट आ रहा है, जो दूसरे पोल की वजह से रिस्पॉन्स है, वो काफ़ी स्लो है. तो इसको आप कंसिडर करेंगे, जो जल्दी डीके कर रहा है इसको हमको नेग्लेक्ट करना है. ओके, व्हाई इज इट सो? Because you can just think of example like if there are two people. Okay, there are two people, they are asked, there is person A, there is person B, and they are asked to reach certain destination point. They have to reach some destination point. Okay, they are given a task that whenever both the people, both these person, when they reach the destination point, only then we can say that the task is completed. Otherwise the task will be said to be incomplete. Okay, so suppose for person A, he reaches the destination in suppose 10 minutes. Person B, he is reaching the destination in 1 hour. But the condition is that the system will be, the task will be said to be completed only when both these person they reach the destination. तो आपका जो ओवरऑल जो टास्क है वो किसकी वजह से स्लो हो रहा है या किसकी वजह से लेट हो रहा है? कौन जिम्मेदार है कि आपका जो टास्क है वो कंप्लीट नहीं हो पा रहा है जल्दी? इट इज़ ड्यू टू पर्सन बी, द वन हु इज टेकिंग लार्जर टाइम. ओके, तो वैसे ही जब हम कंट्रोल सिस्टम की बात कर रहे हैं, हमको ट्रांजिएंट रिस्पॉन्स या स्टेडी स्टेट रिस्पॉन्स की बात करनी है, तो हमारा सिस्टम में जो आउटपुट आ रहा है, दिस सी टी, if I draw it with respect to t, then the output will come out to be like this. When this reaches the steady state, जो आपका steady state at t equal to infinite आप define करते हैं, and this is where the transients are taking place. तो हम ये transient time जो आ रहा है, ये किसकी वजह से स्लोअर हो रहा है। यहाँ पे ये जो ट्रांजिएंट आपका आया है ये किसकी वजह से इतना आया है। सपोज आई एम सेइंग सेम थिंग, इफ इट इज कमिंग एज 1 आवर, ठीक है, आपका ट्रांजिएंट टाइम जो आ रहा है 1 आवर आ रहा है। अगर ये पोल नहीं होता, ये बी वाला पोल, सपोज यहाँ पे जो आप देख रहे हैं, दिस हैड दिस P1 पोल नॉट बीन इन द पिक्चर, देन द आउटपुट वुड हैव बीन रीच्ड अर्लियर ओनली। आउटपुट जो होता है वो आपका काफ़ी पहले रीच हो जाता है, बट ये P1 की वजह से जो आउटपुट है वो बाद में रीच कर रहा है। Okay, hence when we are having this overdamped case, the pole that is further from the origin, that will be neglected. The pole which is nearer to the origin, the time constant due to the nearer pole will be taken, and that will contribute to the time constant. Okay, or in some cases what we do, we neglect the we remove the pole which is farther from the origin. अगर आप इस पोल को ही रिमूव कर देंगे तो आपका सिस्टम क्या हो जाएगा, इट विल बी सम 1 डिवाइडेड बाय s प्लस समथिंग। ओके, अगर आपका सिस्टम ऐसा आ जाएगा तो इसमें आप बोल सकते हैं दैट दिस इज बिहेविंग लाइक ए फर्स्ट ऑर्डर सिस्टम। तो आउटपुट भी हमको वैसे ही मिल रहा है, द आउटपुट दैट वी आर गेटिंग दैट इज ऑल्सो लाइक फर्स्ट ऑर्डर सिस्टम। So this is how you can describe an overdamped case. Now I will quickly revise all the cases that we have seen for, so far. Okay, so if I want to plot the graphs for all the cases that we have seen, we took the input, the input that we are taking, it was sorry, the input that we are taking, we took unit step, hence I'll just mark one over here, this is the input, and I'll just draw all the waveforms that you have when the system is undamped, underdamped, critically damped and overdamped. For undamped case, there is no, the value of zeta is equal to 0, hence the output that you will get a oscillating curve. तो आपका जो आउटपुट आएगा वो ऑसिलेटरी नेचर का होगा। The output that you will get, it will look somewhat like this. Okay, this is going to be the output when the system is critically undamped, for this zeta value is equal to 0. Now if some zeta value is given, कोई damping आप introduce करते हैं system में in such a way that this value, the value of damping factor, it lies between 0 and 1, then the system is going to have underdamped. The system will behave in underdamped as we had seen it, and the output that you will get, it will look like, let me change the pen. Okay, जो आपको आउटपुट आएगा अंडरडैम्प के केस में वो ऐसा आएगा। Okay, and finally it will settle down at 0. Also the frequency of oscillation for this, the frequency of oscillation will be omega d. This system, जब आपका सिस्टम अनडैम्ड है तब वो ओमेगा n की फ्रीक्वेंसी से ऑसिलेट करता है, बट जब आपका सिस्टम अंडरडैम्ड होता है तो फ्रीक्वेंसी ऑफ ऑसिलेशन जो होता है वो आपका ओमेगा d हो जाता है, एंड दिस ओमेगा d इज ऑलवेज लेस देन ओमेगा n। ओमेगा डी की वैल्यू क्या थी, इट वॉज ओमेगा एन अंडर रूट ऑफ 1 माइनस जीटा स्क्वायर। तो आप जीटा की वैल्यू क्योंकि इंक्रीज कर रहे हैं, हेंस दिस ऑसिलेशन फ्रीक्वेंसी इज गोइंग टू डिक्रीज। Anyways, at when this zeta value is equal to 0, only in that case omega d will be equal to omega n. So this is how you will get. आप zeta की वैल्यू सपोज और बढ़ा देते हैं, अगर हम zeta की वैल्यू और बढ़ा देते हैं तो आपका सिस्टम जो है वो जैसे जैसे आप जीटा की वैल्यू और बढ़ाते जाएंगे सिस्टम में डैम्पिंग और इंक्रीज हो जाएगी। ठीक है, फ्रीक्वेंसी भी इंक्रीज हो जाएगी, डैम्पिंग इंक्रीज हो जाएगी, सिस्टम विल स्टार्ट सेटलिंग। ठीक है, एंड when we increase, this is for zeta value between 0 and 1. Now if I increase the zeta value in such a way that zeta becomes equal to 1, तो वो आपका सिस्टम कहलाएगा, इट विल बी योर क्रिटिकली डैम्प्ड सिस्टम। वो क्रिटिकली डैम्प्ड सिस्टम हमारा आउटपुट जो आएगा, इट विल नॉट हैव एनी ऑसिलेशंस इन इट। ये आपका जो सिस्टम है ये इंक्रीज करेगा एंड इट विल फाइनली सेटल एट वन और वट एवर इज द स्टेडी स्टेट पॉइंट, वहाँ पे जाके सेटल कर देगा. सो दिस इज योर केस फॉर जीटा इक्वल टू 1. एंड इफ आई फर्दर इंक्रीज द डैम्पिंग, ठीक है, इसके बाद भी हम अगर डैम्पिंग को और इंक्रीज करते जाते हैं तो आपका सिस्टम जो है वो भी, there will be no oscillations, but the system, it will settle down at 1. But if you want to see, like, among all the responses without any oscillations, which of the response will be the fastest, कौन सा टाइम होगा या कौन से वैल्यू पे जहाँ पे हमारा जब आप सिस्टम में ऑसिलेशन नहीं आ रहे हैं तो आपका वो कौन सा कंडीशन होगा जिस केस में सबसे फास्टेस्ट रिस्पॉन्स होगा. देन वी कैन से दैट ओनली फॉर जीटा वैल्यू इक्वल टू 1, जो कि आपका क्रिटिकली डैम्प्ड का था, उस केस में आपका सिस्टम जो है वो फास्टेस्ट रिस्पॉन्ड करेगा. बट द कंडीशन इज दैट द सिस्टम इज हैविंग नो ऑसिलेशंस. उन्हीं कैटेगरी में हम बोल सकते हैं कि जब कोई ऑसिलेशन नहीं है, उस कैटेगरी में जैसे आप जीटा की वैल्यू और सपोज बढ़ा देते हैं, ठीक है, अगर और बढ़ाएंगे तो ये और ज़्यादा डीके करेगा, और ज़्यादा लेट रिस्पॉन्ड करेगा आउटपुट. तो इनमें से कौन सा वो ग्राफ है, इनमें से जीटा की वैल्यू वो कौन सी है जिसके लिए आपका सिस्टम फास्टेस्ट आउटपुट को रीच करता है. सो दैट इज जीटा वैल्यू इक्वल टू 1. So for sure when you are having any overdamped system, हम जब overdamped system की बात करते हैं तो overdamped system actually gives a very sluggish response. इसकी वजह से जो आपका आउटपुट आता है बहुत ही लेट आता है, ठीक है. it is having very sluggish response, but it is having no oscillations in it. उसमें कोई भी oscillations नहीं होते हैं. So again, as I had talked to you earlier कि हमको सिस्टम कैसा डिज़ाइन करना है, whether it has to be overdamped or critically damped or underdamped or undamped, that all depends on the application. आपका application कैसा है. कई सिस्टम में ये डिज़ायर्ड होता है कि कोई भी oscillations नहीं होने चाहिए. You have to go for the overdamped case. Although the time taken for the output to reach the final steady state, it is higher, but still if the system is not, means it's desired that there should be no oscillation, then you have to go for overdamped case. ऐसे system जहाँ पे थोड़े oscillations चलेंगे लेकिन you want that the output should settle faster, then you can go for this underdamped case. Okay, so I hope that things are clearer to you, and I'll just take one example of second order system. We are going to take RLC circuit. We are going to discuss about RLC circuit. This RLC circuit actually belongs to second order system. Okay. We can have a circuit with resistance, inductance. Let's take this circuit and a capacitance. Okay, and we apply input voltage V into it. This is R, L and C, and we are going to take the output across this capacitance. This is the circuit. Okay. If I want to take this in Laplace domain, then because when we talk about control system, we take everything in Laplace domain. Then what I can write it as Ls, and I can write this as 1 divided by Cs. And the current that will be flowing the circuit will be Is. This is going to be the current. Okay. Now I want to find out the transfer function for this system. My input is this Vns, my output is this V0s. So the transfer function will be what? V0s divided by Vns. ट्रांसफर फंक्शन वी नॉट एस डिवाइडेड बाई वी इन एस कैसे निकाल सकते हैं. यहाँ पे सिंपल आप वोल्टेज डिवाइडर, इस सर्किट में वोल्टेज डिवाइडर रूल अप्लाई कर दो. तो वोल्टेज डिवाइडर रूल अप्लाई करोगे, वोल्टेज अक्रॉस दिस आउटपुट इज व्हाट, दिस voltage across this output is 1 divided by Cs divided by the overall components in the circuit. So that is R plus Ls plus 1 by Cs. So this is going to be the transfer function for this system. Okay. Now I'll just rearrange few things in the denominator. Okay, I can take L divided by S common from the denominator. If I do so, then I'll get inside the bracket I'll get S square plus what? Plus I'll get R by L into S plus it will become 1 divided by LC. Okay, just take L by S common from the denominator. So inside you will get S square plus R by LS plus 1 by LC. ये इसलिए कर रहे हैं क्योंकि हमको S स्क्वायर का जो टर्म होता है इसका कोएफिशिएंट यू कीप इट एज 1. स्टैंडर्ड सेकेंड ऑर्डर सिस्टम से इसको आइडेंटिफाई करने के लिए हमने यहाँ पे डिनोमिनेटर से L by S को कॉमन ले लिया. सो नाउ दिस इज लुकिंग लाइक इट कैन बी रिलेटेड विद द स्टैंडर्ड सेकेंड ऑर्डर सिस्टम. ओके, यहाँ से एस एस कैंसिल हो जाएगा. सो यू विल गेट दिस कैन बी रीरिटन एज 1 divided by LC. Inside the bracket you have S square plus R by L into S plus 1 divided by LC. Okay, or I can write this as 1 divided by LC divided by the same thing. So what was the transfer function that we were getting in the standard second order system? It was omega n square divided by S square plus 2 zeta omega n S plus omega n square. This was my standard second order system. Here what I am getting, 1 divided by LC divided by S square plus R by L into S plus 1 by LC. Okay. Now if I compare these two, I can compare these two very easily. So 1 by LC is equal to omega n square, or I can write that omega n is equal to under root of 1 divided by LC. This is omega n. Similarly, this 2 zeta omega n, this can be compared with this R by L. Already you know that omega n की वैल्यू कितनी है? Omega n की वैल्यू है under root of 1 divided by LC, and this should be equal to R by L. So hence you can find out what is the value of zeta from here. Zeta की क्या वैल्यू आ जाएगी? R divided by 2 under root C by L. यही आएगी. So this will be the value of zeta. Okay. Now when you have this system, जैसे आपके पास ये सिस्टम है, आपको ये सिस्टम डिज़ाइन करना था. सपोज ये कहा गया था टास्क वाज टू डिज़ाइन एन RLC सिस्टम. ओके, आपने RLC सिस्टम डिज़ाइन कर लिया. नाउ बेस्ड ऑन दी वैल्यूज़, हियर यू कैन सी दैट बेस्ड ऑन दिस वैल्यूज़, R की क्या वैल्यू होगी, C की क्या वैल्यू होगी, L की क्या वैल्यू होगी. बेस्ड ऑन दिस वैल्यूज़ यू कैन वेरी द zeta. एंड ओमेगा एन की क्या वैल्यू है? ओमेगा एन इज 1 डिवाइडेड बाय LC. ठीक है, तो आप क्या कर सकते हैं, अगर आपके सिस्टम में L और C कांस्टेंट है, यू कैन वेरी दिस R. ठीक है, बाय वेरिएशन ऑफ दिस R, व्हेन दिस R इज इक्वल टू 0, जब आप R की वैल्यू 0 रखेंगे तो सिस्टम में डैम्पिंग नहीं होगी. सिस्टम विल बी और अनडैम्प बिकॉज देन जीटा वैल्यू विल बी इक्वल टू 0. ओके, देन यू कैन वेरी द वैल्यू ऑफ R कीपिंग दिस L एंड C कांस्टेंट. सिस्टम में कोई इंडक्टेंस है, कोई कैपेसिटेंस है, उसकी वैल्यू आप कांस्टेंट रखें. ये R जो है, ये R आपका सिस्टम में डैम्पिंग इफेक्ट लेके आएगा. क्यों? क्योंकि आपका सिस्टम में जो L और C है, दे आर एनर्जी स्टोरिंग एलिमेंट्स, वेयर एज R इज व्हाट? एनर्जी डिसिपेटिंग एलिमेंट. You can understand it like this, that if you are having this circuit, okay, if you are having this circuit R, L and C, if this there is no resistance, अगर यहाँ पे सिस्टम में कोई रेजिस्टेंस नहीं है और आपने सिर्फ इनपुट दिया and you want to find out the output, if there is no resistance, then these two are what? They are actually energy storing elements. So what will happen? This inductor will give its energy to capacitor. When this capacitor charges fully, then it will again give back its energy to the inductor, and then again this inductor will give it to capacitor, and it will go on without any waste in energy, matlab without any dissipation of energy. There will be no dissipation of energy, okay, in this case. So this case can be taken as when zeta is equal to 0, because the value of R is equal to 0. There is no damping at all. System is oscillating with the frequency of 1 divided by root LC. But if now I introduce this resistance having some value, if this now resistance has got some value, then what will happen? There will be some dissipation over here. So when this energy transfer is going on from here to here, then at in each energy transfer level there is going to be certain dissipation. ओके यहाँ पे आपने एक डैम्पिंग लेवल लगा दिया है, तो वो सिस्टम जो पहले इस तरीके से ऑसिलेट कर रहा था, नाउ द सिस्टम इज गोइंग टू हैव सम डैम्पिंग. ये ऑसिलेशंस जो है ये आपके फाइनली डाई आउट होने लग जाएंगे, एंड अल्टीमेटली दिस इंडक्टेंस कैपेसिटेंस द रेजिस्टेंस दे विल हैव सम फिक्स्ड वोल्टेज अकॉर्डिंग टू द वोल्टेज डिवाइडर रूल. ठीक है, जब आप आर की वैल्यू अगर आप सपोज बहुत ज़्यादा बढ़ा देते हैं, उस केस में क्या होगा कि हमारे सिस्टम में जो चार्जिंग हो रही है इंडक्टर कैपेसिटर की, वो इस तरीके से होगी कि दैट देयर वोंट बी एनी एक्सचेंज ऑफ एनर्जी. ठीक है, जब एक्सचेंज हो रहा है तभी ऑसिलेशंस आएंगे. जब कोई एक्सचेंज नहीं होगा तो सिस्टम जो है वो फाइनली चार्ज होते होते एक स्टेडी स्टेट पे रीच कर जाएगा. बट फॉर डूइंग दिस इट्स गोइंग टू टेक टाइम. जो आपका सिस्टम है थोड़ा सा स्लो हो जाएगा. सिमिलरली in case of mechanical systems also, when you have mass damper spring system, there also the mass and the spring, they are energy storing elements. The damper is the energy dissipating element. So if you have got the damper element, then the system is going to have, you can design it in such a way that it can be underdamped, overdamped or critically damped. But if there is no damping factor in the system, in the circuit, आपके सिस्टम में कोई डैम्पर नहीं लगा है, तो सिस्टम पूरी तरीके से ऑसिलेटरी बिहेवियर शो करेगा. Okay, I hope it's clear, but if you have any doubts or queries regarding this topic, then please do ask me, and we'll discuss it in the live lecture. Okay, thank you.